Okay, so I want to give you a picture for the type of situation, not exactly yet, but the type of situation in which we're going to actually want to use determinants. Okay, I mean, sometimes we want to know determinants of matrices, but here's a incredibly simple example of when I might want to calculate a determinant. Okay, so I have this matrix B. It's just a 2 by 2 matrix, and its entries are 1, 4, 2, and that's a K. Right? So I don't know what this number is. And I could ask the question, for which value K is B is this matrix B not invertible? Right? Let me just ask that question, right? Because we've talked about this, we did this back in chapter 1, things like this. I could use reduced row echelon form, or I could use row reduction to answer this question, but I want to answer it in a different way, right? For which values can I plug in for K, right, and make B not invertible, the matrix B not invertible, right? And I could calculate the determinant of B to answer that question. I know the determinant of B is going to be 1 times K minus 2 times 4, which is K minus 8, right? And I know that B is not invertible if K minus 8, if the determinant is equal to 0. Okay. So that would tell me what? That would tell me K is equal to 8, right, would be a value. And then if we go back, we already knew that, right? Because if K is equal to 8, then my matrix is 1, 4, 2, 8. The first row is a multiple of the second row. The second column is a multiple of the first column, right? It's everything that I know out of that, right? And then ultimately, the question will be something like, oh, okay, I know which value K will make this thing not invertible. And then I might ask a question like, well, what's the null space of B? Okay. It would be the thing that I'd be interested in, okay? So that's the sort of thing that we're interested in, but we're actually interested in a slightly different context, right? So let me give you a matrix. Let me see. You look at my notes here to make sure I am going to use the matrix. Yep. Okay. Something fairly simple. So I'm going to use this matrix A. Okay. So I have this matrix A, which is going to be 1, 4, 2, 3. Now, of course, I can compute the determinant of A. That's not the problem. And this is a non-singular matrix, right? This is an invertible matrix. The determinant is going to be 1 times 3 minus 2 times 4. It's going to be 3 minus 8 when I do that cross multiplication, which is going to be equal to negative 5, right? Negative 5 is not equal to 0, so I know this matrix A is invertible, okay? But that's usually not the question that we want to ask, especially as we move forward to chapter 5, which is all things eigen, right? And so actually, what we'll be interested in is a new matrix, which is called A minus lambda I. Okay. I is the identity matrix, as it always has been, right? A is just this matrix here, and lambda is just a scalar, right? I'm just not going to tell you which scalar it is right now. Right? If lambda is equal to 0, then it's just this matrix right here. Okay? And if I think about it, A minus lambda I would be my 1, 4, 2, 3. That's my A minus lambda I. Well, I is some number times 1, 0, 0, 1. Okay, right? It would be, how do I multiply a scalar times a matrix? Well, I multiply it term-wise, right? And so I'd have a lambda 0, 0, lambda here. So A minus lambda I could write this way, 1 minus lambda, 4, 2, and 3 minus lambda. Okay, right? So this process of taking what we call, a matrix A minus lambda I, essentially what we're doing is we're subtracting off a lambda along the diagonal entries. Okay, and you say, well, why would we ever want to do that? We have a whole chapter, actually, not just next chapter, but the chapter after that, worth of reasons why we would want to do such a thing. Okay, but here's what I want to do. I want to figure out for which values lambda can I plug in here so that this matrix is not invertible? Right? I want to know when is this matrix, which lambdas can I plug in so that this matrix here is singular or not invertible? Okay? And again, the best way to answer that question is going to be to calculate a determinant. So I'm going to calculate the determinant of A minus lambda I. Okay? And I don't have to do anything fancy here. I don't have to use cofactor expansion. This is just a 2 by 2 matrix. So it's going to be 1 minus lambda times 3 minus lambda. Minus 2 times 4, okay, which if I multiply this thing out, looks like I'll have a lambda squared, I'll have a minus 4 lambda. You can check my algebra, but nobody can raise their hand to tell me I'm wrong. I'll have a plus 3, and I'll have a minus 8. Okay, so it looks like it's going to be, as long as I don't go off the side of the board here, lambda squared minus 4 lambda minus 5. Okay, and if the question is what values here will give me a matrix that is singular or not invertible, it'll be whenever this quadratic equation is equal to 0. Okay, so I want to know when is lambda squared minus 4 lambda minus 5 equal to 0. Okay, well, this is a sort of question we answer all the time and calculate, in various contexts. I could use the quadratic formula on that, but I did pick numbers that factor pretty nicely, right? That I can factor lambda squared minus 4 lambda minus 5. I know the product is equal to negative 5, right? I could do something like lambda minus something, lambda minus something, factor that, and I can pretty easily see, okay, if I subtract minus 5, and then I have a plus 1 there, minus 5 and a plus 1, I can double check lambda squared minus 5 minus 4 lambda minus 5 equals to 0. Okay, and so I see, okay, this will be not invertible, right? It'll be singular, right? A minus lambda I is singular when what? When lambda is equal to 5. And lambda is equal to, lambda plus 1 is equal to 0, so lambda is equal to negative 1. Okay. Right. Ultimately, why am I going to be interested in those two particular values? Okay. Or maybe I could just go through and check, do I believe that's true, right? So let me just look at the cases here. When lambda is equal to 5, my matrix A minus lambda I, right? My matrix A minus lambda I would be this thing, right? I'm going to subtract 5. I'm going to plug in 5 for lambda here. So it'd be 1 minus 5, which is negative 4, right? And 4, and 2, and 3 minus 5 is negative 2, right? And I can see the first row is a multiple of the second row. The first column is a multiple of the second column. Yes, it will absolutely be singular. The determinant of this matrix is equal to 0 now. That is correct. And then for lambda equal to, what did we say, negative 1? Okay. Then my A minus lambda I would be A plus I, right? So in this case, I would add 1 to each of these entries. 1 plus 1 is 2, and a 4, and a 2, and a 3 plus 1 is 4. Yeah, and actually the first row is equal to the second row. The second column is a multiple of the first column again. So I can see, yeah, it's definitely a singular matrix there. Okay. Notice it wasn't easy to necessarily see that, right? If I started with this matrix right here, what number could I add to both the diagonal entries to make the first row a multiple of the second row, right? That wasn't going to be necessarily easy to do. To take a matrix like this and do a reduced row echelon form to try to figure that out like we would have back in chapter 1, with those lambdas hanging out there, is not going to be such a nice thing to do. But this determinant gives me a fairly nice way of doing this thing, right? Where at least I can turn it into a quadratic equation. I can factor a degree 2 polynomial, figure out where its roots are, which, by the way, finding roots of polynomials are not an easy thing, right? 2 by 2, not bad. 3 by 3, a little bit worse. Imagine I was trying to do this with a 10 by 10 matrix. I would have a polynomial of degree 10 here, and that's not particularly easy to find. A 10 by 10 matrix, maybe if I have this polynomial of degree 10, maybe I approximate its root using Newton's method or something like Newton's method. But approximations might be the best thing I have, right? So we will, when we're going to answer questions like this, and so we oftentimes will stick with 2 by 2, 3 by 3. And if we really need to do this for a 10 by 10 or 100 by 100 or 1,000 by 1,000, by the way, Google ranks pages more or less by doing these sorts of calculations for trillion by trillion matrices, more or less, right? Then we would use some sort of technology to help us do that. Okay? And so then the question would be, just to follow this one up and finish it off, is let's say I know that when I plug in lambda equal to 5, right, this is the matrix I have, which is singular, which is not invertible. I might ask the question about the null space of A minus 5i, right? And I could say, oh yeah, I could find a basis for A minus 5i, and it would be a vector like 1, 1, and that's going to be an important vector, right? That's the vector I can multiply by this and get the 0 vector, right? And I could ask a question about the null space of A minus a negative 1 times I, or A plus I, and I can see, oh, I can find a basis vector. I usually put a 1 in the free variable, right? And I've got a negative 2 there, right? That would be a basis for the null space of A plus I. Okay. And as we progress into the next chapter here, which I'm going to stop here and we're going to go into the next chapter, these two numbers here, 5 and negative 1, are going to have a special name. We're going to call those eigenvalues, right? Like I said, all things eigen for what. Those things are going to be called eigenvalues. And then these vectors here, like 1, 1, and negative 2, 1, those are going to be called eigenvectors. Right? So the eigenvalues would be the numbers that would cause something like this to be not invertible, singular, right? Meaning something's in its null space other than just the 0 vector. And then those things that are in the null space that aren't just the 0 vector, those things are going to be called eigenvectors. Okay? And eigenvalues and eigenvectors are incredibly important in a lot of areas of mathematics. And we are, at this point, going to spend most of the rest of the semester dealing with eigenvalues and eigenvectors to sort of see what's going to happen with them, how we can use them, why are these things so important. Okay. So we'll stop there, and the next time you see me, I will be introducing chapter, what are we going into next? I will be introducing chapter 5, I believe. Okay. Thanks.